All right, so we left off talking about linear transformations, and we were trying to show this linear transformation preserved scalar multiplication, the homogeneity property. So here we define our linear transformation in this manner. T of x1, x2 is equal x1 plus x2, x1 minus x2, and 2 times x1. So I wanted to show that scalar multiplication was preserved. So we started off here by multiplying through, before we did the transformation, by our scalar alpha. So we got this vector, and then we applied the scalar transformation. So now it gave me this vector in R3. And then from here, I can go ahead and start factoring out an alpha 1, or excuse me, an alpha from the 3 elements inside this vector. And now we get something like this. All right, and then again, using just properties of vectors here, I can factor out the vector and represent it like this. We get all right, and now this is here, the x1 plus x2, x1 minus x2, and 2 times x1 is just t of x1, x2. So we could see here that scalar multiplication does hold. Here, so the above function here is in fact a linear transformation. All right, now keep in mind, this is not always going to be the case, right? Just because we define something with a t and give it some kind of rule does not mean that it automatically is a linear transformation, right? So we do have to check, right? Unless we're told it is linear, we do have to check that those properties hold, right? So let's say, for example, we define this function, we'll call it now, of t of x1, x2. We define it to go to x1 plus 1 and then x2. Okay, so if we check addition, right? So we're going to check if the addition property holds, right? First by performing the addition before the transformation. So if I do that, let's see, I get this vector x1 plus x2. Excuse me, x1 plus y1 and x2 plus y2. And now I'll perform the transformation. All right, and that leads me to this vector x1 plus y1 plus 1, and then x2 plus y2 as the second element in this vector. So now let's test creating the transformation first, and then adding the vectors. So if I do that, our first transformation becomes x1 plus 1, and the second element is x2, and then that next transformation is y1 plus 1, and y2 is the second element. And now I'll add the vectors, and you could see here that in doing that, I do not get the same thing here. All right, this vector is not going to be the same as this one. So we do not have a linear transformation. It represents some function and some type of transformation, but it is not linear because it does not satisfy the additivity property. Okay, so now let's take a look at a couple of theorems that we can describe linear transformations with. The first one is this theorem LTTZZ. And what this theorem states is that linear transformations take 0 to 0. Okay, so it states that for any linear transformation, the transformation from a vector space U onto a vector space V, the zero vector in U is transformed into the zero vector in V. All right. And again, it's going to be important here as we kind of work with these linear transformations here that we understand if we are inside the transformation, right, that is an element in the domain. So here, the zero vector is from the vector space U. Once the transformation is applied, right, and there's no more t, it's just the transformation of it, that vector is in the codomain, in this case, the vector space V. And we can prove this straightforward here by just applying vector space properties and the properties of linear transformations, right? So if we start here, right? So again, here 0u is in the domain, and then 0v is in the codomain. All right, so now let's start with the transformation of the zero vector from the vector space U. All right, now using properties of vector space, I can rewrite the zero vector as the scalar 0 times any vector u in the vector space U. Okay, so here that's just from vector space properties. And now I can use linear transformation properties in that scalar multiplication is preserved. So I can, in a sense, factor out that 0 and multiply by the scalar after the transformation is performed. All right, but what you want to keep in mind is this t of u is a vector in the vector space V. So now I can use vector space properties here, right? So this is in V, right? It's a vector in V times a scalar 0. So applying my vector space properties, I get the 0 vector, but now I'm in the codomain, right? In the vector space V. And that proves our theorem here. Okay, so this is also a practical way to prove whether a transformation is linear or not, because if this condition doesn't satisfy, then you know right away that it's not going to be a linear transformation. Right, and we could have done this with our previous example, right, where we defined the transformation in this manner, and we could see, well, what if I took the 0 vector? And we could see that we get the vector 1, 0, which is not the 0 vector. And we could have made the conclusion there that it is not a linear transformation. All right, our next theorem is going to deal with linear combinations. So it has to do with linear transformations and linear combinations. So what this theorem states is that linear transformation commutes with linear combinations. All right, so that means that a linear combination in the vector space U is a linear combination through the transformation in the vector space V. Right, so what this states, if we have a linear combination of, let's say, t vectors, all right, and the linear combination as it's written here is in U, well, this linear combination commutes onto V because, again, the linear transformation properties, right? I can rewrite this, right, using the scalar multiplication property repeatedly, right, and the additivity property repeatedly. So we get something like this, right? Again, just by linear transformation properties. So the linear combination commutes from one vector space to another, right? All right, and an application of this, right, is once we know T on a spanning set, we know T on everything, right? So if we know what T does to a particular spanning set, then I know what T does to any vector, because again, any vector can be written as a linear combination of a spanning set. Again, notice it didn't say a basis. That is a special case of this, but just any spanning set, right? If I know what T does through a spanning set, I know what it can do to any vector. All right, so now here we've seen that a linear transformation preserves addition and scalar multiplication, and that the zero vector always goes to the zero vector. And linear combinations, they pass through, right? They're linear combinations in U, in the domain, and they pass through as a linear combination into the codomain. So next we're going to take a look at the connection between these linear transformations and matrices.